Да, сделано.
Ага, спасибо.
Okay, so my name is Constantine Taranin. Слышно?
Отлично. Извиняюсь.
Да, хорошо слышно.
And
Okay, let's start. Yeah. Start, please. Yeah.
all right.
Constantine, you may start now. Yeah.
Okay, thank you. My name is Constantine Taranin, and today I'm going to present the results of my PhD thesis. The topic of my PhD thesis is values of the permanent function of 0, 1 matrices and minus 1, 1 matrices. My academic advisor is Professor Alexander Peterman, and I am from Moscow State University. So my dissertation is based on the following 4 papers. They are all in the relevant lists by the Высшая аттестационная комиссия. I don't know the English for it. So these are the contents according to how they go in the main text of the dissertation. And so I think I will start from the definition. Perhaps someone doesn't know. So let R be the set of real numbers. Well, generally we can consider a general field, but I will deal primarily with not just real, but even integer numbers. And so consider the set of square matrices. Then the permanent of a matrix, the permanent function on the set of matrices is, well, it's defined, as you can see, as the determinant, but without the minus 1 to the power of permutation sign. So it's it's the sum of all diagonal products without altering the sign. Generally speaking, permanence can be defined for rectangular matrices as well, but traditionally in the majority of the papers and problems, square matrices are considered. Well, I guess because the results can be generalized without problem onto rectangular matrices, like most important results. So I also deal with square matrices. So as I mentioned, permanent looks very similar to the determinant. The definitions are similar. And for the determinant, we know like possible applications and the computation methods. But what about the permanent? Well, it turns out that permanent can be used, and it is used in such areas as graph theory and combinatorics, linear algebra, economics, like that was inside mathematics, and now outside mathematics, also in economics, genetics, and quantum physics. And later I will tell about applications in economics and quantum physics. So in the first part of my talk about economics, and in the second part about quantum physics. So the application in economics is related to the area of economics called matching theory. As far as I know, is a part of larger area in economics called mechanism design. So in these areas, so like in matching theory, the general setting is the general problem that is considered is the problem of matching, say, candidates and companies, or brooms and brides, universities and entrants. For instance, we can consider the simplest case when the preferences are binary. So there is a preference that connects the company and the candidate when the candidate fits to the company, and the candidate himself likes the company. So we can draw a bipartite graph. One part of the graph will be the set of vertices that correspond to the companies, and the other part of the graph will be the vertices that correspond to candidates. Say, let it be M companies and N candidates. And the edges would be the preferences. So there is an edge between a company and the candidate if there is a preference, if and only if there is a preference. With this bipartite graph, we can associate the adjacency matrix. Generally speaking, there are two ways to associate, to draw this adjacency matrix. The first will be like put all the n plus m vertices vertically and horizontally, and then put unities on the entries where there is an edge. But in this case, that will be a block matrix that will have two blocks of zeros and two blocks of something non-trivial. So basically, we can omit those blocks of zeros and consider the main part of the matrix, which corresponds to drawing just m vertices horizontally and n vertically, and putting unities if on the entries which correspond to the preferences. So companies, candidates, 0, 1, something like that. And the bigger matrix would be like this: 0, 0, and here it will be the same as here. And it turns out that the problem of matching the candidates and the companies, that is assigning each candidate to some company so that either all vacancies are filled or all candidates are hired. It depends on whether m is greater than n or n is greater than n. So the solution of this problem exists if and only if the permanent of this matrix is above 0. And the number of solutions is actually the permanent itself. So yeah, these are these results. They were proved about 100 years ago, I think. Now, as we have now partially seen, permanents are used, and I will also discuss the application in quantum physics later. But what about calculating the permanent? Like, what if we could calculate it just as quickly as determinant in polynomial time and be done with it? And like, there's no point in studying it. And indeed, the determinant and the permanent have a lot in common. The Laplace expansion is true for both. The value of the permanent doesn't change under line permutations. The value of the permanent doesn't change under transposition. And if some line is multiplied by a number, the same happens to the value of the permanent. However, there is one very important difference from the determinant, which is that the permanent is not preserved by one of the Gaussian elimination transformations, namely adding one row to the other with some coefficient, or adding one column to another with some coefficient. And generally speaking, permanent is not multiplicative. Like, it's not correct that permanent of AB equals permanent of A by permanent of B. Another not really pleasant thing about the permanent is that its geometric interpretation is much less intuitive. But one of the advantages is that it can be defined for rectangular matrices. But I have this. And it turns out that this this difference from the determinant, it makes well, apparently, it makes it impossible to apply the Gaussian elimination to calculate the permanent. But moreover, no other method has yet been suggested that could calculate the permanent in polynomial time. The fastest known method belongs to Herbert Reiser. He invented it in 1960s, and it calculates the permanent in n squared by 2 to the power of n. So it's very slow. Another interesting thing is that computing the permanent is a sharply complete problem. So it makes sense to try to study the values of the permanent when it can be done. For instance, for discrete matrices, 0, 1 matrices and -1, 1 matrices are the simplest examples. And yet they have a lot of applications.
Constantine.
Yeah.
So, sorry, whether knowing that the matrix is a 0, 1 matrix can help in computing the permanent, or it is the same for arbitrary matrix?
Sorry?
Если мы знаем, что наша матрица это 0,1 матрица, это не делает вычисление перманента более эффективным, чем для произвольной матрицы?
Нет, no. It doesn't. It was proved by, as far as I remember, Valiant. So yeah, calculating the permanent of 0,1 matrix is not easier than of an arbitrary matrix. There is an area that like about the conversion between the permanent and determinant as well. Like people were trying to calculate the permanent by finding a matrix which has the same determinant. And even this method, it doesn't really work. So it is possible for a very small class of matrices. I can't really tell now for which particular class, but I know that it's not that big.
Another question. What about just finding if permanent is 0 or not? Not permanent, but just finding that permanent is non-zero. Is it more simple? Is it simpler than general question?
For 0,1 matrices, there is a criterion that the permanent is 0. Well, it works not only for 0,1 matrices. It works for any matrices with non-negative entries. So the permanent is 0 if and only if there is a submatrix of size P by Q such that this submatrix contains only zeros and P plus Q is above N, where N is the order of the matrix.
Okay, so it's, yeah, okay, it's too simple. Yeah, I see.
And for -1 matrices, like if you add negativity, it becomes, I couldn't say, like it's not that simple.
Thank you.
So apparently for 0,1 matrices, it can be straightforwardly shown that the greatest value for a matrix of order n, 0,1 matrix of order n, is achieved on the matrix that consists of only unities, and this value equals n factorial. The smallest value is 0, and I've just described for which matrices it is attained. So just to repeat, it equals the permanent of 0,1 matrix as well as any non-negative matrix equals 0 if and only if there is a 0 submatrix of order P and Q of size P and Q such that P plus Q is greater than N. But what about the values between 0 and n factorial? One particular question that was studied by other scientists earlier is where does the permanent of 0,1, like on the set of 0,1 matrices, where does the permanent stop taking consecutive values? Meaning that like 0 is attained, apparently. Unity is also attained. We can just on identity matrix. 2 is also attained if the order of the matrix is 2 or greater. And where does it stop? The first result, answering partially this question, was proved by Brody and Newman in 1965. So they proved that for any non-negative integer j below 2 to the power of n minus 1, below or equal to, there exists a matrix, a 0-1 matrix for the n with permanent equal to j. The proof is quite elegant, I would say. So as far as I remember, they wrote the columns, so like full column of unities, another full column of unities, and then the number of unities decreases by 1 each time until it gets to 1 unity. And then they fill the upper row with like, okay, if you fill it with unity here, you get permanent 1. If you fill it with zeros only, you get permanent 0. And after that, they just fill it with 1 with unity here, and in the remaining part, they write the binary representation of j minus 1, and this gives permanent equal to j. However, this is not the best we can get. And in my dissertation, I proved that it actually, the bound of these consecutive values is actually not less, well, it's actually above than 2 to the power of n. The proof is not that well. This proof is also not that easy. It might seem easy after you've seen it, but I don't think that it was easy to think it from like initially from scratch. Here proof is a bit more technical, so I guess I will just describe the idea that here we have certain chains of matrices which are also related to each other via some one row, and they have consecutive values, like for instance 0 to 30, and then we have another chain that begins with 30 and ends with like, for instance 72, and so on. So the point is, when we have such chains, they have a property that allows us to multiply the set of values that they the set of values of their permanence by 2, and add all the values that are next to each other, like 29 and 30. So after. So if it was like 6 by 6, then when we get to 7 by 7, we get the range from 0 to 144. Okay, this part was about the small values of 0-1 matrices.
Just about, can you say a few words about the proof? Do you construct matrices with all these intermediate permanents?
Yes.
Mm-hmm. Clear. Okay. Thanks.
All right. This was about permanence with small values, because 2 to the power of n compared to n factorial is almost nothing. And another thing that I proved is the bound on the number of large values, which are comparable to n factorial. To show these results, and actually to show the results about -1 matrices as well, I will need the following notation. I define the lower integer part of the number as the closest integer from below, the upper integer part as the closest integer from above, and the integer part as the closest integer. So it might be either from below or above, depending on which is closer. Now, the main result concerning the large values is that the number of such large values, and large here means that it is above the greatest odd permanent. So this is this number that you see here. This is the greatest odd permanent. And the result is that the number of permanents above the greatest odd permanent doesn't exceed this number. The most important part here is this one. So the order of the number of values above this number can be estimated from above as n-1 factorial, but actually, as I have shown recently, by proving the lower bound, the order of the order of lower bound was also n-1 factorial. So actually, which actually tells us that this upper bound is well, it is good, although perhaps this part can be improved. Okay, so this result, the proof of this result is based on the following formula. It expresses the permanence through the number of sets of J zeros or minus unities, depending on which kind of matrix we consider, either 0-1 matrix or -1-1 matrix. So Kj is the number of zeros or -1s that without 2 of them in a line. So like they should be positioned diagonally with respect to each other, or like -1s. For 0-1 matrices, this formula was proved by Boraldi, but for -1-1 matrices, I had to prove it myself. So if you see the useful observation here would be that if we consider -1-1 matrices, like A is equal to -1, then it will be -2 to the power of j, which will be useful for the part about -1-1 matrices. But for now, we are talking about 0 matrices, so let's proceed further. Now, how that formula was obtained? I mean this one. So first, I found matrices that have the property of that their permanent is the greatest not divisible by either p if p is prime or j factorial if j is not prime. This was done with the help of this formula in turn. And after that, I calculated the permanence of these matrices. Some of them were like they're not really, they cannot really be presented in a compact way, but the general form, the general expression through this formula is really useful, and these numbers have some like the representations have some useful properties that allow to estimate them from above. So the idea is that if the permanent is the greatest not divisible by p, then all the permanents that are greater, they are divisible by p. And thus the number of such permanents is very limited. And the limit is actually something about this. So that's the idea. Yeah, these are the greatest odd permanent and the greatest not divisible by 3 permanent. So this is the end of the part about 0-1 matrices. And further, now I will tell in the same order, like first about applications, then about the results. About -1-1 for -1-1 matrices. So as I already mentioned, -1-1 matrices are used in quantum physics. Their usefulness for quantum physics was discovered not that long ago. So you see that this paper is it was written only 12 years ago, and it says that in this paper it is shown that the geometric measure of quantum entanglement can be expressed by a permanent, and it allows to interpret the permanent as the angle between the vectors. Another instance is from another paper. So it connects the result in quantum physics called range criterion with the permanence of -1-1 matrices. So the range criterion is actually not a criterion, it's necessary condition. It states that some state, quantum state, is, if some quantum state is separable. So okay, first I think I need to mention that quantum state mathematically is expressed as an operator on a Hilbert space. So now quantum state is separable. If quantum state is separable, then the range, like the image of the quantum state of this operator contains, well, I don't remember what particularly, but it contains something, and it can be expressed in terms of some linear system. This linear system has a matrix, and the matrix of this linear system, like each element of the matrix, has a sign. So if we write down the sign portrait, we will get a -1, 1 matrix. And it turns out, it was shown in the paper by Kimke and Na, that if this matrix has a 0 permanent, it is also called vanishing permanent in literature. So if the permanent vanishes, then the system has no non-zero solution, and thus the state is entangled. It's not separable. Now, how do we check? How can one check the fact that the permanent vanishes, that it is equal to 0 for a integer valued matrix? One of the ways to do that is to try to divide this permanent by something. And now we can use that useful observation that the formula that I presented above is kind of a expansion of the permanent by the powers of 2, which hints at a very particular way of checking divisibility, namely checking the divisibility by the powers of 2. And although this formula was not known 40 years ago, yet somehow scientists found, they guessed maybe that it's convenient to try to divide the permanent of -1, 1 matrix by .
Ау, Константин, у нас что-то все пропало.
Да, я тоже ничего не слышу.
Константин, а у нас нету, ничего не слышно.
А может, вы позвоните? Вы знаете какие-нибудь...
Я не знаю, как связаться.
Борь, ты знаешь какие-нибудь координаты?
Я могу только письмо написать, да, сейчас я попробую написать.
Мгм.
Настя, Настя, а может быть, Константина удалить из беседы, и тогда он заметит, что что-то не то?
В смысле, что значит? Я не понял, чего ты предлагаешь?
Но, может быть, он нас тоже не слышит, и если его удалить из
Удалить это
Zoom,
его как участника.
да, он поймет, что что-то не то.
Ну, да, ну что, удалить его, да?
Наверное, да.
Ну, хорошо, пытаюсь. Написано, что once removed, Constantine Taranin will not be able to rejoin the meeting.
Это не очень удачно.
Не то, что мы хотим. Да. Сейчас, вот я могу попробовать его put in waiting room.
Простите.
Вы
Я
появились.
что-то... Да, я что-то отключился.
Да, значит, примерно последние минут 5 мы вас не видели.
Минут 5. Так, хорошо.
Там было сказано, что какие-то результаты все тестировались, а потом сказано, а вот свои результаты мы сейчас скажем ниже, и все пропало.
Так, какая страница?
Вот это была
Вот
последняя
примерно вот
страница.
это вот. Сейчас.
Вот.
А можно воспользоваться перерывом и спросить у вас, вот ваш результат про то, что я как не успел сообразить, ваш результат про то, что там в интервале от n плюс 1 факториал делить на n и делить на e до n плюс 1 факториал, там сколько-то значений перманента. Это
Да.
как сравнить первое число со вторым? Много значений перманентов в этом интервале или наоборот очень мало?
Еще раз, какое значение с каким?
Ну вот ваша теорема, которая говорит, что в интервале от n плюс 1 факториал делить на n и на e до n плюс 1 факториал, да, есть не больше, чем сколько-то значений перманентов.
Так.
По-моему, ваша большая вторая теорема. Или третья. Вот эта оценка, это как она сравнивается с длиной интервала? Это вы говорите, что очень мало значений перманентов в этом интервале или не очень мало?
Мало. Она, длина интервала получается где-то сейчас сколько? 2/3 n факториал.
Да. А по вашей оценке сколько?
А перманентов получается где-то 0,4 n-1 факториал.
Понятно. Да, понятно. Спасибо.
То есть более чем в n раз меньше.
Да, понял, да. Спасибо.
So, okay. Okay, so Hazel, yes, Kreuter and Zeifter proved already 40 years ago some results on the divisibility of permanence of -1 matrices by the powers of 2, but they did it with the help of really complicated work of Hazel Perfect. And in my dissertation, what I've done is I proved the results of Kreuter and Zeifter directly with the help of formula that I have shown. And besides, I also proved a criterion of divisibility of the permanent by a greater power of 2 than it was studied before. So now I think it should be more clear when I show the results themselves. So this is the first result by Kreuter and Zeifter. They proved that for all n of this form and all matrices from well, this is actually denoted by omega n. It's the set of all -1 matrices of order n. They shown that for all such matrices, their permanents are divisible by 2 to the power n-t. They also shown that for all such matrices, their permanents are not divisible by 2 to the power n-t plus 1. And for all other n, like for n of other form, permanents of all matrices from omega n are divisible by n by 2 to the power n-t plus 1. And apart from proving these results directly, I have also shown that matrix, the permanent of a matrix from omega n is divisible by 2 to the power n-t plus 2 if and only if the sum of kj, remember that formula. Yes, here it is. So the sum of certain kj is divisible by 2. So the sum over which set, the question is. This is actually the set that contains all non-negative integers j or m. Here they are denoted by m, such that the binary representation of n minus m has exactly t minus 1 unities. The good thing about this set is that it actually not that big. It never has more than t elements, And for a lot of n, it may contain only one element. Like, for instance,
А что такое k с индексом m?
Yeah, okay. K with index m is the number of sets of j elements -1, such that they are situated like on the diagonal. Like, there is no pair of -1s from this set that are on the same line or on the same row. So this is prohibited. So this is the number of diagonally situated sets of j -1s. For instance, for n of the form 2 to the power of t, it is just k1, which is just the number of the number of negative entries of the matrix. So it's really easy to count them and to verify whether the permanent is divisible or not by this power of 2. And another corollary is that for any natural n, there exists a -1 matrix such that its permanent is not divisible by 2 to the power n minus t plus 2. How to see it? Well, just consider the minimal element of M, and consider then the matrix that has M, like, denote this minimal element of M by M0. Consider the number of minus unities. Consider a matrix that contains M0 minus unities on its main diagonal and unities elsewhere. So apparently it will be the permanent that is not visible by this number. And another set of results about -1 matrices. Well, it's actually one result. And it will be the last my result that I'm discussing, and it is the last result of the dissertation. It concerns directly the direct verification whether the permanent vanishes. So previously I tried to divide it by something, and it will be like direct classification, but for n equal to 5. So for n equal to 1, it can be straightforwardly seen that there is no matrices with permanent 0. For n equal to 2, there are exactly 8 such matrices, all the matrices that contain odd number of minus unities, -1s. And for n equal to 3, again, there are no such matrices because 3 is the number of the form 2 to the power t minus 1. Well, 1 is actually such a number. Now, classification assumes some equivalence. So I call the matrices equivalent if one of them can be obtained from the other by permuting rows or columns, transposing or multiplying some rows and columns by -1. So all the operations that do not change the absolute value of the permanent. Since we are interested in zeros anyway. This result for n equal to 4 was proved by the same researchers, Kimki and Na, the ones that proved one of the interpretations of the permanent in terms of quantum physics. So, but in their paper, they didn't consider equivalence up to transposition. So actually, they have 5 matrices, and as you can see, one of my matrices is symmetric, and 2 are not symmetric. So actually, if I give up equivalence up to transposition, I will also get 5. So the result.
Насколько велики орбиты?
Well, it's a good question, but they are huge.
Вообще группа эквивалентности, она какого размера?
Permutation of rows is n factorial, permutation of columns is n factorial. Then changing the sign is 2 power n.
Yeah, but you see, some of them might coincide.
Right. Yeah.
That's not.
But like for large n and for general metrics, for small sizes, it should be counted by hand. But
well, yeah. But I tried to do the same thing for n equal to 6, like to choose one matrix for each equivalence class. Well, of course, I didn't manage to do so, but anyway, I was left with not that much matrices that initially I had. And yet my computer was classifying them for 3 days. So it's a lot. But the results concerning n equal to 6 are not in the dissertation. So yeah. So basically for n equal to 4, they found that there are 3 classes of matrices with permanent 0. And I found that for n equal to 5, there are 11 classes of matrices with permanent 0. How I proceeded, like first I tried to throw away all the matrices that are equivalent as much as possible. Then I also used the criterion that I proved. It helped a lot to narrow down the number of matrices to consider. And then I was left with some very small number of matrices to consider by hand, and that's it.
And where is the class of the matrix with all ones, the equivalence class here?
The equivalence class.
I don't think it gives 0.
It doesn't give 0. Yes.
You need
it's permanent. It's not determinant.
I see. I see. Well, sorry.
Yeah. So this is the final result. This is the list of all results that I mentioned today and that are included in my dissertation. So again, it's the improvement of Browdy-Newman estimate. It's an estimate on the number of values above greatest odd permanent. It's the criterion of divisibility and proof of direct proof of Kreuter results, as well as the formula for decomposition by the powers of minus 2 of 2, and the classification of matrices of order 5 with permanent 0. Thank you. If you have any other questions, you are welcome.
Thank you, Constantine. Other questions, comments? I have questions of myself. What is the correct replacement of the Browdy-Newman estimate which you expect? Is it, for example, n-1 factorial or not? Or how close is your estimate to the optimal one?
Yeah, that's a nice question. Thank you. On the one hand, when I was looking at this problem, like using the approach that gave me my estimate, like the belief that I got is that it should be some power. Well, it shouldn't be factorial. However, like my most recent work, already after the dissertation, it's about large values again, like the lower estimate. Yeah, the lower estimate for the same number, and the methods that I used there, they hint at the, well, they give the intuition that perhaps the number of permanents increases as we go like from n factorial. The density of the permanents increases very much as we go from n factorial to smaller values, and perhaps perhaps it will be something greater than power of anything. So it's a good question for research.
Thanks. More questions?
I have some naive question. Is it true that the largest value of permanent, which I guess is achieved on the matrix with all ones, is achieved only on this equivalence class of this matrix, as you explained?
You mean
all matrices that can be obtained by permuting rows, columns, which is the same, and multiplying rows and columns by negative ones.
What kind of matrices?
Matrices from negative ones and ones. Yeah.
Negative ones and ones. Yeah.
Yeah, because if it's 0, I guess it's if it's 0, 1, I think it's clear, right?
Yeah,
that the largest value is only. Yeah, but if matrix from negative ones and ones, so is it unique matrix where you achieve the maximal value of permanent, or you have more classes?
Isn't it obvious? We have just 10 factorial summons,
Yeah.
and each summons is 1
Yes.
by absolute value.
If there is some disbalance between positive and negative, like if there is at least one negative member, then it will
Well,
be below.
you can take
Yes.
matrix from with ones and multiply
Yes,
two
I
rows
see.
by
Yeah.
negative one, so you will still get the same permanent.
Yeah, of course. And
The question is it any other operation which is not kind of in U equivalence class which does the same?
Yes, it's not. It's a nice
So
question.
it's not idiotic question, right? It's not clear.
No, it's not clear. It's not clear.
And second question, are there any application of your upper bound, right? So you said that you have like the theorem that you show. So oh no, not this one, the previous one, that you have you have upper bound of the interval when permanent takes values like 1, 2, 3, 4, and so on, right? So what applications of that? Are there any application of this result outside of this just studying properties of permanent? Do you know any applications?
As far as I remember, there were some. This is related to the study of what is its name? There was another function in that Broldi and Newman paper that they studied, and this function, like it has some applications, but I don't remember.
You mentioned something about number of solutions of some problem, right? That the number of perfect pairings.
Yeah. Well, that's generally application of permanence of 0-1 matrices. But whether this particular question, like how, of course, yes, we could think of a way to connect this particular question to this particular problem. But I guess there were other applications in the Brody and Newman paper as well.
Thank you.
One more question. Indeed, a few questions. If you consider -1 matrices, then how many equivalence classes are there? How quickly does the number of equivalence classes grow with the size of the matrix?
The number of equivalence classes.
Да, количество классов смежности, классов эквивалентности, как растет для -1 матрик. Это известно?
As far as I remember, it's an open question.
It's an open question, yeah.
Yes.
And for example, consider the following functions. Just take the interval from 0 to 1, split it into 100 segments of equal size, and consider all the matrices, all the 0-1 matrices whose permanent is divided by n factorial falls into such a segment. Then you obtain a function whether there is some limit distribution this function. You obtain a distribution of permanence, whether this distribution has a limit as n goes to infinity.
So the question is whether there is a limit.
Yeah.
I guess it is also an open question. Basically, that's what I'm trying to do in my latest work. Like start studying this issue. Like from the it can be shown that there is always a permanent from X to X. Yeah. And a good question is how, like, if we consider X and then 1 plus alpha X with alpha from 0 to 1. So how small can alpha be? And like if the answer is different for different parts of the interval from 0 to n factorial, then which is the smallest alpha for like each, like how alpha changes from 0 to n factorial? That's an open question.
Okay, and there is a traditional question: which problems are you going to address further? What are you working on?
Well, this problem. And the related problem of the limiting distribution that you mentioned. Another problem. I remember that there was another problem. Yeah. So another thing that we can do is consider -1, 0, 1 matrices. And well, this brings together all the difficulties that we have with 0, 1 matrices and -1, 1 matrices. So there's another set of problems here.
Okay, thanks. Are you done?
Спасибо, Костя.
Спасибо. Thanks everyone for coming.
Спасибо.
Можно отключаться.
Наверное, да. А скажите только, у вас что-нибудь, да, не знаю, что-нибудь, да, каким-нибудь определились, нет пока?